Okay, and I didn't go into full math details because we can always go deeper into math later on, right? But we're data scientists. We want to do things too, right? We actually want to try things out. So let's try to implement this in actual notebook. And so I think the curriculum first goes into like doing it from scratch or something, but I'm just going to go dive into sklearn because I'm just going to use sklearn. Like I never drive it from scratch, but it's important to understand where these things are coming from. So, all right, I have this kind of put together. I have my NumPy, my pandas, good old NumPy and pandas, right? I have my matplotlib, just so I can plot a little bit later. sklearn, so note this guy right here, basically it's just so I don't want to generate my own data. I'm not very creative on the fly. I don't have data set, so I'm just use sklearn's data sets. So I'm going to pull data that already is built into sklearn. And then we're just going to do some extra stuff, so doing some modeling. So I'm going to do normalize because you have to normalize your points here. So instead of me normalizing it, like the curriculum shows, I'm just going to use sklearn because it's already there, right? And then I have logistic regression, which is going to be the actual model, right? So this is going to build up our logistic regression. So very similar to how we did linear regression. And then, of course, our train test split. So I'm pretty sure Raphael already talked about this, but train test split. Why do we do a train test split? Can someone just really quickly just summarize, like, what's the whole point of that?
To confirm the accuracy of our model.
Yeah, right. It's we split our things basically so we don't we can confirm that we're not seeing things that don't actually exist. The way I kind of describe this is when we do a train test, you can think of it like your model is like a student learning. And it's kind of like your train, it's kind of like the practice test, you know, and the stuff that they kind of practice and they go over and over and over again until they get it right. And then their test is kind of like the actual test they have like in the classroom to see how well they understand the material. If you give like the actual test that they'll take and you give it to them, you know, as homework and they study the test over a week, right? And then you just give that same exact test like in school, you don't know for sure if they just memorize the answers or they actually understand the material, right? And that's what we're doing. We're basically making sure that our model is not going to see this testing data. I just wanted to reiterate because this is not just for logistic, linear regression, or anything like that. That's pretty much for all machine learning models. And this guy right here, doing your split, is something that data scientists, machine learning engineers sometimes really mess up by accident, you know, and or just maybe naivety, right? And bad things happen where they think it's really great and it turns out it's not. So always important to do this. But moving on. All right, so let's actually go ahead and play with some data. So I'm going to load the iris data, which is a relatively small data set. You'll see it a whole lot. I'm just making a data frame so we can see it really quickly. Oh, I didn't import this. There we go. There we go. And now we have this guy, just to kind of quickly see, we have the data frame right here. You can see there's like 1, 2, 3, 4 different features. And we have our target, and our target's going to be classification. So it's going to be either 0, 1, or 2. So there's 3 different classifications we can do. And then you can see sepal length, sepal width, petal length, petal width. I'm no biologist, I'm no botanist, but basically from my understanding, if I remember this right, this is about like, you know, like the flowers and stuff like that and classifying, oh, like how big are these flowers? Okay, I don't know, does anyone know what sepal is by chance? Okay, that's right. It's a thing, right? It's some feature. So we have our sepal length, our sepal width. We can see there's 150 in here. You can see basically this distribution. Cool. All right. So let's go ahead and just, oh, like I said, there's only 3 targets, 0, 1, and 2. Okay. So that's basically what we're trying to predict is like, is it 0, is it 1, or is it 2? So let's go ahead and just kind of plot this out just to see what the distribution is for each point. So we're going to look at each feature. And we're just going to look at saying, okay, well, these are the different classifications, 0, 1, 2. I just did a little subplot right here so we can actually see that the distribution of each one. So you can definitely see there's a general trend in sepal length. So it looks like 0 tends to be relatively small. Then we have 1 that's kind of medium, and then we have 1 that's longer, right? So you can now see this general pattern. But we can also see that there's also some crossover, right? So like if you were to combine this together, if you had a value like right about here, it would probably be either 1 or 2, but you wouldn't know which one, right? So this is kind of just visualizing what this difference is. But you can see for petal width, we can almost looks like most of it, we can determine most of it from petal width itself. There's still some crossover, but definitely less. So this is always a really quick, good EDA to check out. All right, so let's go ahead and prepare this so we can actually do classification. All right, so what I'm doing here basically is just getting the features and the target. So I'm getting the features separately and the target separately. That way I can like keep these separate. So X and Y, and just to kind of show you guys, This is X. So you can see here this part. And note that also, even this is a data frame, sklearn actually uses NumPy arrays, but why can't I just use a data frame even though it's asking for a NumPy array? This is bad. Can I do this? The secret is data frames are just NumPy arrays. So that's really why we can do this. So I sometimes get people say, can I use a data frame? Or like, oh, do I have to make it a data frame before I pass it in? Like, as long as a NumPy array and data frames in series are NumPy arrays, you can just pass it through. Okay. So, all right. So there's X, and then of course Y is just going to be the target itself. You can see zeros through ones. Okay. Cool. All right, so let's normalize it. So the reason why we normalize this, it just helps the model converge faster and stuff like this. It's not technically for logistic regression, it's not necessary, but it does help. Some machine learning algorithms, as you guys will learn later on, actually require some of these values to be normalized, or you can only take values between 0 and 1. And this is something you have to kind of consider when you're pre-processing. But in this case, it's not necessary, but kind of helps us kind of converge the model quicker. And then we do our X-train split. So X-train, X-tests, doing my split. Note that I'm using a test size 20%. That's pretty standard, right? And then random state. You guys know about this random state for train test split? Give me a thumbs up if you guys seen this before. Thumbs down if you haven't seen it before. No, okay.
We've seen it, but can we get a refresher?
Yes, definitely. So test train split, and you guys know about shift tab, right? All right, cool. All right, I was going to blow someone's mind if they didn't know. So yeah, shift tab so we can kind of see this documentation, right? But basically, test train split, we have our X, our Y, right? So our training, I'm sorry, not our training, our features, our target, our test size is saying, okay, how big is our test size? 20%, right? So there's other features we can pass, or features, parameters we can pass in here as well. Random state, oh, I see a little chat guy. What we got? Sorry, Alex says, I've seen test train split only using 2 groups. Only thought of this, I would say train set, test set instead of X train, X tests. Yeah, so, okay, I'll go into that part too. So Alex mentioned is that he's only seen this as 2, like, separated by commas, but I'm seeing 4 different things. I think that's what Alex is saying. I'll get to that in a second. But one thing I want to say, random state, you should, as a data scientist, to make reproducible data, your random state is basically, this is your seed. So you guys know about random numbers and seeds? Okay, gotta see head nods. So basically this is to ensure that we always get the same random numbers, which sounds kind of like an oxymoron since they're random, but it means that basically we do have random numbers, but they're pseudo-random numbers, so that way we can always get the same thing. That way we can make sure we're not testing, when we're training our model over and over and over again, we're not doing something, we're not getting better results because of randomness, we're actually getting better results because our model's doing better. So it's good practice to set this random state. Does that make sense to people? Okay, if I didn't change this random state, it would just randomly try to pick a seed essentially and give me new random numbers. And I couldn't tell for sure if I reran this again, if it was because I got a new train test split just by chance, or it was because something my model was doing. All right. Cool. So this guy right here, the reason why this happens is why I can do this X train, X test, Y train, Y test, is you can kind of see, let's see if I can quickly see what my returns. Returns a list containing train test splits. That's not helpful. It's easier just for me to show this way. Okay, so let me show you what happens here. So you can see here, this is an array, and actually I can do, let's just do all equals, oops, that's a reserved word, I can't do that. So let's just do shape. Oh, it's a list. Oh, everyone. This is why I don't code on the fly, because I press the wrong buttons. There we go. All right, so the length of 4. So what happens if I can do this? Like, okay, you can see I just saved it as 4 in here. So for example, if I just did the length of the first element, it's 120. Second element is 30. 120, and then 30 again, right? So what it is basically the first element in that list is my training data, but just the features. Then it gives me the targets of that training. And then it does the the test set. Oh wait, do I have this right? I'm sorry guys, I'm messing myself up. Oh, I might have this backwards. Wow. Ta-da, now it's fixed. All right. Wow. Past Victor is awful. All right. So you can see here, basically the very first element in this all part, it's just all of the training, right? Or the features for the training set, right? And then if I go to 2 here, you have the actual, no, I had it right. I'm sorry, everyone. Wow. Present Victor is awful. Past Victor is correct. All right. The first set basically is saying, okay, this is, yeah, sorry. I messed myself. I was confusing myself. Hope I'm not messing you guys up. Too bad. But this is the size of X train, right? So in this list of 4 different items, it's going to be X train, X tests, Y train, Y tests, right? So you notice that I just did all here, which is the same as this guy, but I just did all. In Python, you can actually just say, hey, like if there's multiple like tuples, or if there's a list, you can actually say, hey, just give me the first element, since I know there's 4 in here. So if I just do len of all, there's 4, right? So what you can do, if I did instead, let's just try train, let's just talk X and Y, and we do, just copy this guy. This will still work because basically, oh, no, actually this won't work. I'm trying to think if there's a reason why you would have this instead. Alex, I know you mentioned if you've seen 2 before, but maybe you've seen it differently. This is how I typically go through. Does that make sense? I think I'm going into a little bit of a tangent, but basically what's happening here, does using normalize do the same thing as using a log transform min-max, or are they all separate? That's the part I've been kind of foggy on since mod 2. Oh, okay, that's something separate. Let me just kind of finish this up real quick, and then I'll address that. Just know that basically train test split will return, you know, a list, right, of your training set, your testing set, sorry, your features of your training, your features of your tests, your target of your training, and your target of your tests, right? And so if I did all like this, I can keep the whole list, or because it's a list like this, I can say, well, okay, let me just split up each 4 parts. So I don't have to go, okay, like I could have done X train equals X, oops, equals all 0. I could have done this and then do that for each one, but that's kind of annoying and I don't want to do that, right? So that's why I had it like this. Okay, does that make sense to people? Hope I didn't confuse you guys more in something that maybe you guys already knew or didn't know or whatnot. I was thinking there's a tuple part, but I guess not. I usually do this anyway. All right, going back to Alex's question, using normalize. Okay, so does using normalize do the same thing? I'm just going to copy down here so you can read it too. Oh, you guys can all see this. What am I doing? That's fine. Okay. Does using normalize
library is normalized from?
I'm sorry?
What library is normalized from?
sklearn, I believe, is what I'm using here. So sklearn.preprocessing. Okay. So you can normalize, it says do the same thing as using a log transform, min-max, or are all these things separate? So yeah, these are, so does using normalize do the same thing as using a log transform, min-max, or are these all separate? They're all separate ways of doing things. Normalize, remember, is going to basically squeeze it into a normal distribution. And so it's going to scale it down so we have our standard deviations. Like it's going to transform so we have the standard deviation of 1, and our mean, if I remember this right, is set up to 0 on default for sklearn. Min-max are going to be different. It's not going to separate it out by its standard deviation. It's just basically saying the minimum is going to be like 0 and the maximum is going to be 1, which is very different, right? So min-max, if you min-max transform, it will stay at 0 and 1, right? You cannot have a value higher than 0 or a value lower than 0 or a value higher than 1. But normalizing, we could technically have something that's 12 standard deviations away. So it'd be 0 plus 1 plus 2, you know, plus 1 plus 1 plus 1 plus 1 plus 1. It'd be a value of 12. So it's slightly different. We can also have the opposite direction. A log transform, basically you're applying just the logarithm on the value. So like the log of 10, log of 12, whatever values you have, and you're just transferring that. That tends to scoot things off to the side. Like for example, I think you guys might have used it for like skewness and stuff like this sometimes, because very large values will go very small. Basically, the logarithm is a very slow monotonically increasing function. It's actually the slowest monotonically increasing function that we can write. And so what that basically means, if I was like, whoa, that was a lot of words I wasn't ready for. Basically, it just means is that it goes up really, 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 really slow, right? So if I do something like, again, hopefully I'm not making, this is all good stuff, right? So I can do NP log, right? So NP log of like 10, right? Sig2. What if I do to the power of 100, right? Let's do I do like power of 20, right? It's like, okay, like this is like 1 followed by 20 zeros, right? Must be huge. Oh, it doesn't do it. It's too big. Let's just do it manually. There we go. So you can see how many zeros, and it's only 23. So it's a very, very slow increasing function. I don't know how big I can get. So that's the reason why you have to use a double. That's okay. There we go. So you can see here, however many zeros that is, it's only 43. So that's why we can do that log and it squeezes it over. So log transform can be really helpful when you have values that are really extreme off to the side and it scoots it over. Okay, cool. Any questions on those things that I kind of mentioned? They're not quite related to this, but I think they are useful since there are transformations that you might use.
So the normalize function, it just does mean normalization?
Yeah, it should be. Let's see here. Let's do, what do we do?
Yeah,
Normalize, right?
I looked it up once you told me it was sklearn. That's what it sounds
Perfect.
like. It does.
Yep, unit norm, vector length. So yeah, you can definitely look into more. Documentation is super useful. As you can see, like you can just pull it up here, or of course, literally just search sklearn normalize, right? But in general, we talk about normalize.
Basically, it makes every point into units of standard deviations.
That's right. Yeah. So your standard deviation is always 1.
Yep.
Cool. All right. Cool. So let's move on then to actually doing this logistic regression. We got about 20 more minutes left, so I think we can get through it. All right. So this is the best part about modeling with sklearn. It's like super short, right? We did all this processing, right? We took the data, we got our targets, we got our features, we split them into X-train, X-tests, right? Note that I'm adding some extra parameters here. You probably could do this perfectly fine. These are basically just things to kind of help us, move things like make sure things can go through. For example, solver, I'm just saying, oh, use this solver. You could basically just use the defaults and that's probably fine. I'm also doing fit intercept just so I can have it consistent. You don't have to have this part, but it's kind of like with the fit intercept for linear regression. You have some values, basically you start pulling that information into the intercept. I won't go into full detail, but main part is basically our model is going to be logistic regression. We have this guy, and then we say, okay, this, oops, I actually have to save it to the right thing. Pass vector, what are you doing? Oh no, I'm right, okay. Our logistic regression, we do a fit, X train, Y train, and that's going to do our model. And you can see here, if I run this now, boom, I fit it. All done, right? So you can see how simple that is basically. And essentially that's just saying, hey, go ahead and take logistic regression and go ahead find with the solver, right? Find the best logistic regression curve that's gonna fit on this data using NLE. That's essentially what we're doing here, okay? And then that's what that dot fit is. We have this fit on the train data, and now we actually wanna test it out, right? Say, how well did it do? So we're gonna go ahead and see y hat test, right? And then y hat train. So the y hat train should be more accurate than our test, hopefully, right? Because it's trying to optimize as best it can on the train part. So I'm doing a prediction off X tests. And this is where I'll tell you is that if you remember these parts right here, this makes it really easy. You can replace this pretty much with any model that you want, machine learning model. And the process of dot fit with sklearn and then dot predict is basically identical. I could have designed my own algorithm and stuff like this. So you'll see this kind of process over and over again. Okay, so let's go and do predictions, right? So we already trained it, right? So this is just saying, hey, what was your prediction? So let's go ahead and evaluate this. So let's just check out the training, right? So how many basically did it get correct, right? Our Y train, right? Which is what the actual true values are. Our Y hat is our prediction train. So this should hopefully be pretty close. We might get a couple wrong, but we should hopefully have it pretty close. And we can see here, all right, 117 of them we got correct out of the 120. So that means basically Y train's pretty good, right? And over 97% accuracy, probably closer to like 98 point something. Okay, so let's go see what I have. This percentage of values correctly predicted. Oh, Oh, good, 97.5. Okay, so just giving it in a different way. Okay, you guys know about this value counts normalize, right? Equals true. Yeah, super useful. All right, let's see about, we don't care about the training though today. We're really talking about the test, right? How well did we do on this school test? And residuals is just going to be y test equals y hat. So you're going to be true or false. And let's see how we did. All right, cool. 28 out of 30, right? That we actually got correct, right? And we can actually check that out, normalize it, say, oh, 93% accuracy, at least based on our testing data set. Okay, now this is a really small data set too. So there's obviously some issues with that. Like, maybe if we had more testing, we'd see that we'd have a lower accuracy, or maybe we'd see a higher accuracy. Okay, cool. Makes sense to everyone? Like, if we went down, at least how to code this part. Yeah, awesome. Any questions before I move on to some evaluation stuff?
I might have missed it, but how did you determine the split between training and testing?
Like this guy right here?
Oh, okay, so it determined like an optimal split for you.
Right. It's random in this case, random by my random state. So
Oh, are you able to find out what is being used? Or I guess we just know from the numbers, right? That,
right. So are you, when you say like, when you're doing a split, right, you have like all your data, right? And you have to define some of them as your testing data and some of it as your training data, right? So I'm splitting where 20% randomly chosen, just of all those, values.
I'm
Taking
sorry,
20%
yeah.
of it.
Yeah.
Yeah.
0.2 or 0.8, I guess.
Right. And that's why we have, I think it was 120 and 30, right? So 30 is 20% of 150. So,
okay. No, I was just wondering if that split was predefined or if like some algorithm determined.
yeah, the algorithm is it's random, like if that makes sense.
Yeah.
Of course, I could change the random state and it won't pull me the same thing. So just to kind of show you guys, like if I run this again, like and do everything, it should still give me the same exact things because it's the same split. But if I change this to, let's say, I don't know, 72, we should get maybe slightly different values. And you can see here, 115 out of 5 for the training. And if I go down here, we can see, oh, in this case, all 30 were correct. So 100% accuracy, right? So this is why, for example, you want to put a random state, because you want to make sure if you have the right random state, you might just by chance be better at your algorithm, right? Or your model might do better. But that's why we always want to have it consistent. That way we can always improve and double check that, hey, is this actually, am I doing it? Or is it just because it's random? Does that make sense? Cool. All right, awesome. So anyway, this is basically, that is logistic regression, right? You're like, oh, not bad at all. Like most of my work actually is getting the data, pre-processing it, but the actual training itself is like these two cells. Like that's all that is. And that's really what's interesting about machine learning, is that basically you are providing all the inputs first, right? And then saying, okay, well, let me give the parameters maybe for logistic regression or whatever machine learning model you have, and then go ahead and fit on it. And once it's fit, you're kind of done, right? Your computer's doing all the optimism, doing it itself. It's obviously a little more complicated than that, because you have to figure out like, how do you, tell the computer, how do you solve for this? How do you like find the best answer? But generally that's kind of how it works. Now the next part, which I'm going to go into, we only have about 10 minutes, but I'll go through parts of it, are, what's it called? This, sorry, I just realized too. No, I didn't. Okay, never mind, sorry. So I thought I didn't record it and I didn't see a little button, but we did. The next part we're gonna do is just talk about evaluation, this part, which is actually probably the biggest part of machine learning, that sometimes this is super exciting, like, ooh, look how well I did. But you need to figure out how well did the model actually do? And is it accurate to say how well it did do? Accuracy is usually not the best thing to quote. There's actually a few other ways we can do this.